I'm going to talk about resilience. So this talk started normally a talk of performance or specific details, but we had a client who recently moved to Vitess from another database, and they said they were able to add 1.9 to their HA. So I said, hey, we build resilience, but so what are the things within Vitess that have been used to build resilience? So for me also, it was a learning session in some sense. I've been a Vitess maintainer for 6 years. Work at PlanetScale, which provides cloud services on top of Vitess MySQL and recently with Postgres. I'm also working on the sharded Postgres, which is very early stages. At some point, hopefully, we'll make it open source and be available. Oops. Technical hitch.
The slides are on a different machine because I see 2 mouse pointers.
No.
Did you figure it out?
Yeah, just to, I think many of people I've met, I've realized over years, didn't know what Vitess was. They've never heard the term, but actually it's running a lot of database structure that everybody is using on a daily basis. So Slack uses it, a significant portion of database, I don't know how much percentage.
100%.
100% of MySQL is run over Vitess. GitHub pulls and issues are run on Vitess. Uber, anyone from Uber here? So yeah, do you know which part of, I think it was Eats, but I'm not sure. Some part of Uber is using Vitess. Cursor has recently moved their code-based metadata from Postgres into Vitess. Finted, Etsy, Cash App, there's many such things. So just to show you that, it is something that a lot of people are using. And so the idea of scale is very important in terms of resilience. So we need to provide HA and Vitess at this scale, right? Slack had 3 million QPS. This is about a couple of years ago. GitHub is over 5.5 million. This is queries per second, right? We have databases over tens of terabytes, petabytes. There are tables sharded like 256, 512, even 1024. So PlanetScale, which has thousands of clusters, many of them are very small, but they're also really big clusters. We have peak QPS of tens of millions. So we have to provide availability at the scale. So let's talk about what is resilience. People throw nines, across. What does it mean, right? So even 99, which is considered not very great for critical systems, is just 14 minutes of downtime per day. This includes maintenance windows, everything. When if you talk of 5 nines, it is 5 minutes a year. So practically extremely difficult to manage. Typically, people we have seen operate at between 99. So 95 to 99, so up to 4 nines. That's also pretty hard. So we have to build in right from the architecture, design, implementation, that we are able to recover from issues really, really quickly. And it's not just downtime. If you have a latency, if a query takes a minute instead of 5 milliseconds, it's down, right? Similarly, throughput, if your QPS goes from million to 100,000, it's down. So it's not just about being hard down, it's also performance. A lot of implications. Cost is a clear issue. Critical services. This is a good time to talk about resilience because 10 days back, AWS was down, right? And luckily I was on vacation, but my company, everybody was up through the night trying to figure things out. And we did okay. We can do better, and we are figuring out how to do better. But 2 days back, Azure went down, right, for a few hours. So when AWS went down, there were people who couldn't move their beds, sick people who couldn't move their beds because it was entirely running on the cloud. Okay, those guys fixed it immediately, giving Bluetooth connection, but why not right up front, right? So that's what I'm talking about when you talk of resilience. So loss of data, of course, And you deal with realities. I mean, you don't have infinite budget. Project managers want you to deliver things yesterday. Trained people in these areas are very hard to find. So these are all the things that also impact. Yeah, this is just a back of the napkin numbers, but just to give a sense of, people talk about hundreds of millions or maybe even a billion, which was lost during the AWS outage. So it's important. I'm not sure how many of you know the cause, but the cause was a DNS misconfiguration of their DynamoDB service, which was used by over 120 internal AWS services. Everybody was storing the metadata in that DB. So single point of failure, right? So I guess people did not expect it to go down for that long, but it did, and it also caused cascading failures. It's not that I'm sure many of our databases also go down like this at some point or the other. It's hard to build everything resilient, but it's a good example of how critical these services become and how important it is to design resilience into your system. Talk a little bit about Vitess, the architecture. So it originated at YouTube, about, I think, roughly 15, 20 years ago. It was intended to scale YouTube. YouTube was not able to serve cat videos fast enough. So they needed, they were already using MySQL, and the founders of Vitess worked in Google for many years. So they built YouTube. So it was working at YouTube scale for many years. And when YouTube decided to switch, I think they switched to Spanner, the founders, they allowed the founders to open source the software, and it's the origin of open source Vitess. High availability, of course, and so at YouTube, it was built on a cloud platform called Borg, which was actually the precursor to Kubernetes. So it is cloud native by default in the sense that we use microservices, and it's intended to use auto scaling, etc., from the services available from orchestration of Vitess for Kubernetes, for example. It's MySQL compatible. It works with a lot of standard like Ruby on Rails, Django, Spring, all the ORMs. It works with WordPress. So underneath, there could be hundreds or even thousands of different databases, either sharded or not. But Vitess provides a single connection to it. So if you have legacy code, you can just point to a Vitess cluster. And internally, it will do the query routing. And it speaks MySQL, of course, and also gRPC. So when an application connects, it connects via load balancer. Load balancer is not part of Vitess. You just use a standard like NLB or whatever. The entry point is VT-gate, which is a stateless query serving component that gets your SQL, parses it, figures out whether, in case it's a sharded database, whether it should go to a single shard or across shards. If it's a point query to a single shard, it will pass it straight through MySQL, because that's the most efficient way to do it, and just returns the values back. If it's cross shard, it will collect the data, potentially do sorting and aggregation for aggregating queries, etc. So it's pretty complex in terms of query serving, but otherwise it's lightweight. That's all it does. And it doesn't talk directly to MySQL. So Vitess has this concept of a key space. It's basically a database, a MySQL database, but underneath there could be multiple shards. So you could have unsharded key space, which is just in a single MySQL replicated setup, or you could have hundreds or thousands of shards. So the sharding key is determined by something we call the V schema, which says which table should be sharded by what columns, a set of columns. And VT-gate knows that. It reads it from the topology service, which typically is etcd, could be Consul or Zookeeper. So depending on the primary key that's coming in or the sharding key that's coming in the query, it'll parse it, figure it out, and send it to the appropriate shards. It only talks directly to a component called VT tablet. So it doesn't talk to MySQL directly. That helps in many ways, some of which we'll see in the context of resilience soon. So VT tablet then sends the query. So they typically sit on the same board in Kubernetes, and they will use sockets for fast communication. Each shard so since we use MySQL, we are able to take advantage of many features of MySQL, like replication. So we'll have one primary, which takes the writes, and multiple replicas, minimum 2, and some have more. And okay, I'll go into details a little more when I'm talking about specific aspects of resilience. Just a quick, this is all conventional wisdom here, but good to know. I've generated few categories of attack clouds here of what can go wrong. VMs, disks, networks can get partitioned, submarine cable gets cut, for example, issues. Packets get dropped regularly. Application bugs, of course, right? And they can end up with CPU use out of memory. So at a system level, we need to handle all this. We cannot, it might come from anywhere, right? But we have to figure out a way to react and respond quickly to these. At the database layer, the replicas might lag a lot. Sometimes people will run a batch delete because they want to clean up something of millions of records, and then it ends up with a replication lag, so which can affect availability. Similarly, issues with clock, sudden load spikes due to a new campaign that starts can cause issues. And very often, both of the last two, where AWS as well as Azure, were linked to a combination of human error misconfiguration and DNS resolution failures. So these happen a lot, right? So how do you deal with it as a system? So just stop me if at any point you want to ask any questions. So these are the sort of principles that you read about in literature about how to add resilience to distributed systems, to systems in general. And it's useful to take that as a model and map it. So we understand, like some of the decisions we know are either instinctively or from experience, but they're all related at a high level to these principles. So isolation, where essentially all the components, you try and make sure that there's zero or minimal dependence on each, right? So that there's no cascading failures. One thing failing, like DynamoDB failing, just led to so many other things failing, right? So redundancy, copies of data across places. So some of this, again, when you read it, it sounds like conventional wisdom, very hard to implement at scale consistently. Over provisioning. Okay. So again, there are costs attached here. So there's a cost to availability, right? So that's in the reality. So I can easily say over provision, but so you might have to carefully over provision. One important principle is try and not to entirely fail, right? Instead of hard down, see if you can degrade gracefully the service. One example is that if the number of VT gates which are serving the query go down, reduce for some reason, you can use what we call circuit breakers, right, to increase the latency. So it will take longer. Each query will take longer. The user will see higher latency, slightly lower QPS, but still there is access. By the way, all of these are tunable. Vitess has zillions of parameters to tune many of these things based on the actual need, because it works from like really small clusters to really massive clusters. So we can do throttling. We can throttle queries. We can throttle processes based on certain parameters. We'll see where they come from. Another approach is that if you have existing connections, let those through. Don't drop them, but drop new connections so that the application will back off and try again. So when you're talking of at distributed level, apps are expected to understand that anything can go wrong. So they have to handle errors that they can see. So typically they back off and retry. Automated recovery, manual recovery simply will not give you any number of nines. So it can escalate a few times a year, but most of the time you try either proactively to avoid the problem in the first place. You see that some components are going bad, and at that point, you can scale up components or maybe kill the components you think are not doing well, so that the system never gets into a bad state or a much worse state. Reactive, sometimes a primary in MySQL replication can just go down, and you need to self-heal it, right? You have to figure out mechanisms to self-heal it. And the last two are, again, obvious and boring, but really critical. Metrics, we give out a lot of metrics for different things like replica lags, CPU usage, etc. And realize that there are thousands, sometimes tens of thousands of components. There are VT gates. So each VT gate usually will do between 2 and 10,000 QPS. So if you have 1 million QPS, you already have like 100 times those number of VT gates. And similarly with tablets, right? If you have 100 shards, you already have like 300 different MySQL instances. So these the number of amount of hardware involved is a lot here, right? So a lot of metrics are coming in from everywhere. Usually there are tools which are looking at some of these metrics. Some of them at some point, maybe you cannot recover from it because it's just a bad actor and it's bad SQL query that's continuously coming in. It's not fixed. That gets paged, so you need to have mechanisms for all that. Testing, of course. So let's go into details of some of these principles. So one of the ways of achieving isolation is Vitess breaks up the cluster into multiple cells, and you would host these cells in different availability zones. If you're just doing it with AWS, you would have, for example, these 3 zones. You could also do it across clouds. So within PlanetScale, we do have at least 2 clouds, certain companies which are on multiple clouds as well. So for each shard, you have primary and multiple replicas. So ideally, depending on the scale and the importance and criticality of the particular service, you would put replicas in different availability zones. Vitess currently has a single primary, so it doesn't have what's called the multi-master for writes. So it's possible that there's a network partition and the primary is not available. But in which case, we'll see later that reads are still allowed within that. There are also ways to get around that. In case you're doing, let's say, a worldwide geo-based service, you can put your customers based on geo-sharding, that Europe has its own customers. So the primary for the Europe shards will be in Europe, similarly for US and Asia. So in that case, only cross-shard transactions, transactions which are across shards in different availability zones will fail, but the rest will continue, service will continue. The topology, HCD also, there's a global topology which has the entire information about the distributed cluster, but there are also local HCDs running on every cell. So so I'm not talking of performance. Many of these also impact performance. They come from there they're in both areas, but we're talking of resilience today. So if there's a network partition, you will still have a topo to connect to. VT gates, when they start, they'll read from the topo, the configuration, but they're not dependent on the configuration we have. They're not continuously reading from the topo. So as the topo changes, they watch the topo, but if the topo goes down so when I'm saying going down, most of the time it's under seconds. Yeah, we're not talking of long periods. because there's corrections that's happening continuously. So even for that short time, you don't want to have a problem with your in a query path. So the topo is not in the hot query path in Vitess. Shard database I talked about in terms of geosharding. Redundancy, we get MySQL replication for free because we are using that as a storage layer. So it's an early decision not to build a new storage layer for this for Vitess. So semi-sync is, so just how many of you use databases? I mean, in the sense on a daily basis. Yeah. Of course. How many of you programmed database who are building? Oh, quite a lot of people. Good times. A lot of it is not new for many people. Yeah. So semi-sync is a feature in MySQL where every write has to be acknowledged by at least one replica before it is returned to the client. So that means that if the primary goes down in between, that particular transaction is available with at least one replica. Sharding, not just for geosharding, but you can also have sharding. Let's say you have 128 shards and you have distributed it based on customer or tenant or whatever. Right? If one of them goes down, it's less than 1% which is affected, which is better than the entire database going down. So similarly, yeah, this is just HCD configuration. So I talked about graceful degradation. How do we do it in Vitess? So all queries from all the VT gates for a particular shard go into the VT tablet, either a replica or a primary. Now, sometimes things go viral or there's a new campaign that comes out. You suddenly get a thundering herd of queries that come in. That can bring down a database if you're actually going to go to MySQL for executing every query. So at VT tablet, you identify that, hey, we have a lot of these queries of the same queries coming in, and you block the others, get one result, and you send that result across to everybody. So that protects the MySQL from a huge spike suddenly. Connection creation is one of the highest overheads in databases. It's orders of magnitude more than running actual queries. So VT tablet provides different types of connection pools. Everything is configurable, the size, TTL and all that is configurable here. Cell isolation I mentioned. You can continue with local cell reads if there's partition. Another big reason some people come to Vitess just for one particular reason is to do schema changes at scale. Right? That's a whole different topic. There are talks on it, but it's basically if you have like 100 billion rows or 1 trillion rows across hundreds of shards, how do you change? How do you alter the table? How do you change the type of a column, add an index? If you try to do it online, it'll bring your database down for hours, if not days in some cases. So the way Vitess does it is you have a shadow table and you run it in the shadow table. Behind there is a module called vReplication that's used in many of these, which essentially copies the table across and then keeps the table in sync with the bin log streams. So change data capture essentially. But finally, at some point, you have to also switch the table internally. Right? I'll come to that. But this process is a huge write amplification. So let's say you have 100 billion rows in a table. You're going to generate 100 billion writes on the shadow table. But that is not critical. So there is throttling, a lot of fine-grained throttling, which can say that, okay, my query serving is going to get affected. CPU usage is high, memory usage is high. Throttle the schema change process. Right? And typically it's fine to do it because it's an application level thing. And so again, you can give priorities and stuff. So that's a very important back pressure technique that is there. It's also used in resharding. So all of this happens online. We'll talk about how, in the sense that there's no downtime involved even after switching. If you reshard from 64 to, let's say, 256, because you find a load is increased, or let's say the end of Black Friday, you want to, come back, because you don't want to use those resources, you don't need them anymore. So you would do a reshard that does again the same copy and the v-replication technique, which I mentioned, copy followed by following the bin logs. And during a switch, so anytime you need to switch, you need to stop writes for a brief while because the target has to completely catch up with the source. So typically, these are all, again, the order of seconds. For extremely complex database, we have a maximum limit as well, which is by default 30 seconds. So that's a lot. But so all of these also get throttled based on the query serving, which is the query serving is the king here, right? So it's something that always needs to be as performant as possible. So during these switchovers, the VT gates, which are receiving the queries, they understand when they see an error that it's a cluster event that's generating an error. Cluster event is like schema change is being switched over, or reshard is being switched over. When that happens, VT gate starts buffering the queries. It says, hey, I'm going to just wait, right? I'm going to keep the queries in a buffer, wait for it. And when the event is complete, let them through again. You throttle it and let them through. So of course, it is increased latency, but there are no errors. And again, to repeat, I'll probably say it many times, but these are all typically in seconds. Right? It's not like a large amount of time. Similarly, for timeouts, if you have bad queries that are coming in, you can set timeouts so that a few queries don't bring down their, like noisy neighbor problem. You can also say that I want to read from replicas because I'm okay with a little bit of staleness, but I'd rather, because they just reads. But VTGate can also be told saying that if the staleness is beyond some time, and the staleness, again, we measure in seconds, right? It's not like very. So you can say 1 second, 5 seconds. Beyond that, VTGate will not consider that replica for the query itself, right? So there are various automated recovery mechanisms. So one, there's a component called VTOp, which I showed you, which monitors the cluster health. This is done, every VT tablet publishes its health, which is essentially whether it's a primary or not, and the various database metrics. So VTOrg is continuously monitoring it. And when it finds, for example, that primary has gone down, right, it will immediately take action. It will do what's called an emergency reparent. It will look up a replica, which is the latest, which has the latest data, and promote it as a primary. And in the same, so Kubernetes and then creates a new replica through backups. So that's the other. So there are many dimensions to this, right? The health checks are also subscribed to by VT gates to find out if a replica is lagged, and to also know like which is a primary at the moment. Backup restores are extremely important because we want to bring new components in quickly, right? One component has gone bad. So we have initial like big backups that you do. And on top of that, you do incremental backups, essentially backing up of bin logs so that something goes down, you can start from the backup and rerun the bin logs and get a new, so you can either do point in time recovery at this particular second, or you can bring it up to the latest state. Smaller shards help. So sharding helps here as well. I'm very keen of hearing the next talk, which talks about 200 terabytes. In Vitess, we basically used to say 250 GB as one single shard size. Now, because of everything, it's increased to like 500 to 2 terabytes. Never have a shard beyond that size, explicitly for reason for which the next talk is going to be given, that backups take a lot of time, right? And you want to be able to recover. So recover point of recovery, you want to be able to recover quickly. So sharding helps a lot in that case as well. So it's not just about performance, resilience. There's also this other aspect of resilience where smaller shards are important. There's also a cost-related thing where you can choose smaller shards because Amazon will give it to you at lower rates. That's also important, but again, not part of this talk. So we talked about schema changes, import, reshard. All of this then use the vReplication layer, and vReplication has a concept of reversible workflows. So let's say you've switched from, take a simple case, like you're doing an import from an existing database, you want to move to sharded Vitess. You are not in Vitess at the moment. And this is a very common use case, people try it out, that's how they try it out. I want to do 4 shards. So when you move to the 4 shards, you suddenly find that performance has dropped like crazy because you're doing cross-shard queries, you're not thought about that aspect of it. Your sharding key may not be right, you may not have provisioned it correctly. So Vitess allows, so when you switch writes to the new target, you can continue to write to the old source. Okay, you can replay bin logs back. So that same manner in which you switched to the new one, you can switch back. Okay, so it's just called reverse traffic. And again, within seconds, you're back to your old. So that's a really important, it's not directly related to, I guess, things going down, but it's an important part of operations. Right? If you didn't have that option, you're in trouble, right? So one of the original things that the Vitess found and the authors was that what we call the regret feature. So this was built pretty early. You don't want Vitess, don't use it, right? If there's a problem for any reason. But that also helps people adopt it because you can then go back and forth, play around with it. Same thing with schema changes. You might drop an index and find, hey, actually this query was using it. And you bring it back, fix the query, then, so VT is the Vitess operator, the Kubernetes operator. So one of the principles that we follow is if something has gone bad, like you have a server going bad, MySQL server, you can try and figure out what went wrong, fix it, and keep the same one, or you can just replace it. So repair, it's too slow, right? So we just call it bad, term it bad, VTORC or Kubernetes will just replace it. So it's again an important principle. Later, you can look at logs. You can we have a way to keep the VT tablet, for example, if it fails in something called the drained mode, so it doesn't join the topology again, but it's kept there for people to do forensics on later. Same thing with VT gate. Sometimes it runs out of memory. It could be a bad query, could be a bug in Vitess, could be often you've also seen surprise bugs in MySQL, right? All the time, especially because we're running tens of thousands of servers. Some bug or the other once in a while comes. It's transient, but it brings it down. So we just replace and life continues. Telemetrics, of course, informs a lot of the recovery mechanisms. We're going to talk much about it. I'll talk about regular updates. That's useful. So typically, let's say you do a software update, there's a CVE, you want to update Vitess itself, right? A new feature, new patch, whatever. So the way we do it is you upgrade the replicas first, right? And then you promote one of the replicas to primary, and then you upgrade the primary, which has now become a replica. You can even add more new ones if required. That all depends on how much redundancy you want. But this makes sure that rolling upgrades are all really easy and they happen without downtime. So within PlanetScale, for example, we have a TTL of 1 month. After 29 days, every node is recycled because when you're working in the VM environment, noisy neighbor, there are various issues because of which it makes sense to restart. It goes against sort of some engineering principle that I learned very early, but that's how it works in this world. There's a benchmarking, this is all open source, available where in a PR you can opt into benchmarking so that if you have, let's say, a query serving change. That's how we catch regressions. We didn't have that for a while, and then we used to end up with regressions. At the end of when we are releasing it, somebody will say, hey, this is 20% slow, 10% slow, whatever. So this is one way we catch it. Yeah. So a different way of looking at it, not just principles, is that I think I've sort of run out of time, but yeah, just quickly go over this. So you can look at architectural decisions, design decisions, mechanisms, right? So some of them choosing MySQL, right? Choosing etcd, choosing sharding as a way to horizontally spread data, multiple cells, stateless VT gate, the VT tablet supervisor of MySQL, right? The VTR component. Similarly, the failover buffering, health check mechanisms, the back pressure throttling. Discuss most of these here as well. So even many of the important things, like when you switch writes, we also have a dry run where it will actually run through everything except the final thing to check in case sometimes certain shards are not available. When we say not available, it might be 5 seconds or something, right? So you don't want to wait that because that's downtime when you switch. You have to stop writes. So then you'll wait and then do it at a later time. So, I think the key takeaway is I think that there are deliberate design decisions made throughout the process. It's not just maybe once in a while some things, low-level things you learn along the way. And of course, we have refactored. It's not that what started 6 years back is different from what is now, but mostly it is the same. And many of these decisions were made with a view on resilience as well, right? So again, same thing, using MySQL, using VTGate, the system partitioning, and failure automation. So yeah, that's pretty much what I have. What is it? Oh yeah, okay. There are a lot of flags and stuff that allow you to tailor your own environment, because everybody's environment is different. Some people might tolerate write loss. Some people want faster latency. They don't want semi-sync, for example. Some are willing to do more staleness of data. It depends. There are gamers who use it, also, so they have a different requirements. Yes. I hope this was useful to some people at least.
Are there questions? Any questions? Fabian?
Yeah, you mentioned the VT gate, right? And you said it could do sorts. Is it just a modified MySQL or is it something that is custom?
No, it's a Golang, completely Golang.
So how does it, why does it?
I mean, if it's cross-shard, right? So if you have cross-shard.
Yeah, sure, but are you guaranteeing that it does exactly the same thing as MySQL? And
That's a fantastic question. We come across bugs of that sort regularly, but over time we have fixed it. And sometimes MySQL does very weird things.
Yeah.
We have to mimic the weird things. So we have to build in bugs that MySQL has so that it matches.
Yeah.
There are actually a lot of fuzzing tests that we do. That's why the fuzzing tests are important, because we have learned behavior, you say why, especially with collations and strings. And so it's, yeah. Somebody who has actually come across this problem, I think.
Thanks for the great talk. So I'm curious, speaking of isolation, do Vitess provide any kind of multi-tenancy built in? Like, can a same user, maybe like two different customer or like completely different users?
Yeah, so you can do it. You can have different databases within Vitess itself. So you'll still see it as a single logical connection, and you can connect to different databases. So people do it all the time. So there are lots of small databases along with the larger databases. So those can be unsharded, right? So there are many databases which customers will have in the same cluster, but yeah, so it's possible.
I guess that, thanks for a nice talk. I guess that making things resilient, you learn from errors, I suppose, because making things resilient is difficult to test. So can you share some war stories on what were surprising things that led to because surely if Vitess didn't work out of the box flawlessly immediately in those kind of stressful situations.
This has come out of
Yeah.
hundreds of years of database experience with the founders.
Yes.
So that is true, right? Exactly. I mean, so war stories, I don't know, Slack, he's recently with us from Slack, he's joined PlanetScale. He's surely seen a lot of things going down here. Putting on the spot, but
Yeah, like our cache, a lot of Slack relies on cross-shared queries that get cached in Memcache. And we had a database issue where it exceeded the TTL of the Memcache. So basically all queries in Slack were hitting the database when we were never sized for that. That was one of the worst ones. Made it to BBC, you know, like newsworthy kind of stuff. That's not really the test though. Yeah, it's a tough question. I guess like the consolidator, in advance of a query, you can't know its result size. So the consolidator doesn't have an upper limit or a very sensible upper limit because it doesn't know how much memory it's about to use. So you can actually your tablets if you have too many consolidations and don't set a limit on that. We had issues with that at Slack.
yeah, I mean, there's other things as well. So this MySQL behavior sometimes is surprising. For example, server might go down and when it comes back up, it will actually write the previous transaction it found where actually, according to documentation, it's not supposed to do it. So you end up with errant GTIDs, two different servers with errant GTIDs. So we have now, I think we have sort of solved the problem now. Last few months I've not heard this, but every 2 months we would have within PlanetScale, one customer, suddenly, you know, you have two different MySQL instances, one replica, one primary, which has got slightly diverged in terms of GTID. And that's, for us, it's an incident, you know, it's people get paged and you look up and try and figure out. So I think we have worked around it. VTORC has been extended for it. That's an example. Another example is very low level one, which I was responsible for personally, as in the vReplication. I was adding some feature and I did a clone of an object in Golang and everything looked fine, everything tested, people tried it at scale. It just brought down this thing because it was ending up using huge amounts of memory. I didn't need to do it. I just, I mean, it just happens, right? Once in a while you catch it. So then it's hard. So one of the good things with Vitess has been companies like Slack. I think now he's at PlanetScale, but he was at Slack for many years. GitHub, HubSpot. So they collaborate very closely on our releases. So they'll run it in their staging. And we also get the benefit of that testing because it's open source. So, and we do catch some things like 2 versions back. There were issues that GitHub had which nobody else had. And Arthur, who's again with PlanetScale, but he was GitHub earlier, he would diligently test these things and he would come back and say, hey, what the hell, you know, this has gone down. And none of our tests showed it. Then we of course add it to our tests, but yeah.
Semi-sync has been a problem with demotions in some reparents where we can't actually acknowledge a write, so it gets stalled. That's something we're working on right now.
Yeah.
Yeah, out of ideas for now.